Welcome to AI Paperslap. No warm-up banter today because we are jumping straight into a massive release from iQuest Research. It's called Loop the Loopies.
Quite the name, I know.
Yeah, but the implications are huge. If you work with large language models, you know the compute accounting problem of loop transformers.
Yeah.
Usually, if you take a model and loop it, say, n times, you just multiplied your pre-training compute by n.
Right, which makes it almost impossible to justify.
Exactly. Because why loop when you could just spend those GPU hours training a larger standard model? But this paper, it actually solves that. The authors introduced two models, Loopie 20B A to B and Loopie 6B A 0.6B. Both are built on a mixture of experts' backbone.
And they completely redesign how models iterate.
Yes, using this layer loop architecture. And then they execute what they call a precise Loopie recipe. They basically slice the number of stored layers in half to free up memory.
Which is brilliant.
And then they weaponize that saved memory to drastically widen the hidden dimensions and increase the microbatch sizes. The result. Loopie strictly matches the wall clock training time of a standard non-recurrent baseline, but absolutely destroys it in performance.
It really does.
Plus, they bypass traditional instruction tuning entirely with a massive supervised pre-training, or SPT, pipeline, hitting frontier-level reasoning and beating NVIDIA models trained on, 7 times more data.
I mean, it is a complete paradigm shift for the ML community. For years, we have treated recurrence and transformers as a parameter-saving trick. You share weights across layers so the model just fits on your GPU.
Right, so you don't run out of VRAM.
Exactly. But no one really viewed it as a compute-efficient trick, because you still had to pay the FLRPs for every single loop. What this team at iQuest did is reframe recurrence altogether.
They prove that it's a compute match scaling mechanism.
Yes. If you architect it correctly, it is fundamentally more efficient to loop locally than to just endlessly stack new independent layers.
So I really want to break down how they actually pulled that off. Because to understand what Loopie achieves, we have to look at the architectural shift first. They completely abandoned standard model loops and moved to layer loops.
Which is the core innovation here.
Right. And for anyone listening who might be rusty on looped architectures, prior models like Aro or Hugin use what this paper considers a fatally flawed design for large-scale training. And that's model looping.
It is a nightmare for infrastructure.
It is. Because if you have, say, 3 layers, and you loop the model twice, the computation flows from layer 1 to 2 to 3, and then it routes all the way back to layer 1, 2, and 3 again.
The entire transformer stack is just unrolled sequentially.
But Loopie uses layer loop. The computation goes layer 1, then layer 1 again, then layer 2 again, then layer 3, and layer 3.
Yeah.
Why is that specific, localized ordering the secret sauce here?
Well, if you are managing a massive GPU cluster, you know that pipeline bubbles are your absolute worst enemy. There are 2 massive reasons why layer loop is superior, and the first is purely about hardware execution locality.
Okay, break that down for us.
When you use pipeline parallelism across hundreds of GPUs, model loop is just terrible. Think about what happens. Every microbatch has to traverse your entire pipeline, and then the output of the final stage has to be physically routed all the way back across the network to the first stage.
Just to begin the second loop.
Right.
So you're introducing massive cyclic dependencies. I mean, the GPUs sitting at the beginning of the pipeline are just twiddling their thumbs, waiting for the data to travel all the way back across the cluster.
Precisely. The communication overhead just destroys your throughput. But with a layer loop, all the recurrent applications of a specific layer stay right there within the same pipeline stage.
You just iterate locally.
You iterate locally. The GPU processes layer 1, refines it again through layer 1, and only then passes the activations onward. It is infinitely more infrastructure friendly because the data doesn't have to fly across the server racks.
Okay, so that covers the hardware side. But there's a functional side to this too, right? Because they claim this localized looping also makes the model fundamentally smarter.
It does. It comes down to parameter sharing and functional coherence. Consider a standard 48-layer model using an old-school model loop. Layer 3 is executed at effective depth 3.
Right.
Then the data goes through 45 more layers, comes back around, and layer 3 is executed again at effective depth 51.
Wow, yeah.
And we know from extensive probing studies that transformer representations vary wildly depending on how deep you are in the network.
Right, because the early layers do totally different things than the late layers.
Exactly. The early abstractions a model builds at depth 3, like basic syntax or token relationships, are completely different from the highly semantic, abstract reasoning it handles at depth 51.
So model loop forces a single set of parameters to serve two completely different masters. You're basically asking the exact same weights to do basic grammar detection and high-level logic simultaneously.
which causes massive interference. Layer loop, by contrast, reuses a layer at adjacent depths, effective depth 3 and effective depth 4.
Where the semantic demands are almost identical.
Exactly. It's a much more natural, local, and coherent sharing pattern for the parameters.
I love that. So for you listening, think of it like this. Model loop is like reading an entire textbook cover to cover and then reading the entire thing a second time to try and understand the concepts.
Right.
But layer loop is like reading a single dense paragraph twice before moving on to the next one. The context is fresh, the vocabulary is the same, so your brain, or in this case, the GPU, processes and refines it much better.
That analogy hits the nail on the head.
Yeah.
You are locally refining the representation before passing it up the hierarchy. It's an iterative polish rather than a complete reset.
Okay, so we established that layer looping works better functionally and prevents your GPU cluster from bottlenecking. But I'm still stuck on the compute math here. How does the team ensure this architecture doesn't just explode the pre-training budget?
Because looping still costs compute.
Exactly. Even if you loop locally, it's still extra FLPs.
This is where we get into the absolute genius of the Loopie recipe. Their stated goal was to match the exact end-to-end optimizer step wall clock time of a standard non-recurrent reference model.
So they didn't just want a theoretical math.
No, they wanted it to take the exact same amount of time in reality. They used a Qwen 3-like 30 billion parameter mixture of experts model as their baseline. To beat it without spending an extra second to compute, they executed a 3-step recipe.
All right, what's step one?
Step 1, they halved the number of stored layers and set the loop count to exactly 2.
Hold on, let me play devil's advocate here. If you cut the physical layers from, say, 48 to 24, but then you loop them twice, you are still doing 48 layers worth of math. Isn't that literally the exact same amount of work? Where is the savings?
The executed math, like the leading order transformer block compute proxy, does stay identical. But you are missing the memory footprint.
Ah, memory.
Yes. For anyone who has dealt with out-of-memory errors during training, you know about activation checkpointing. During the forward pass, you have to save the intermediate states, or activations, so you could use them during the backward pass to calculate gradients.
Right.
Under standard activation checkpointing, your memory scales with the number of stored layers, not the executed depth.
Oh, I see. Because you only have 24 physical layers, you are only storing 24 sets of activations in memory, even though the data runs through them twice.
Exactly.
So by having the physical layers, they essentially slash the activation memory required during training by 50%.
Yes. And in large-scale training, memory is the real currency, which leads directly to step 2. They took that massive chunk of freed-up memory and used it to double the per-device microbatch size.
Let's explain why that matters. In distributed training, you have a global batch size. Let's say it's 4 million tokens, but a single GPU can't fit that, so you chop it into microbatches.
Right.
If you double the microbatch size because you have more memory, you can have the number of gradient accumulation steps required to reach that global batch.
And fewer gradient accumulation steps means less time spent launching kernels and waiting on optimizer synchronizations. A larger microbatch exposes far more parallel work to the GPU at once, making the hardware utilization just spike. The throughput becomes incredibly efficient.
Which gives them extra time.
Exactly.
And here's where the hardware reality kicks in. They didn't just calculate this on a whiteboard. They literally loaded this into Megatron LM, measured the actual wall clock efficiency gain from that microbatch change, and moved to step 3.
Step 3 is the payoff.
Yeah. They spent that measured time savings on expanding the model's physical capacity. Specifically, they widened the hidden dimensions. They took it from 2048 in the baseline to 2304 in Loopie.
So look at what they engineered here. They built a model that is significantly wider, has half the stored layers, loops twice, and because of the microbatch efficiency, it takes the exact same amount of time to process a batch as the baseline.
It is a masterclass in hardware-aware trade-offs.
It really is.
And the results speak for themselves. They ran a massive pre-training head-to-head on 800 billion tokens. Initially, Loopie 20B A to B actually lagged behind the vanilla baseline, but right around the 600 billion token mark, it overtook it and just kept accelerating away.
Just massive gains.
But this raises an obvious question. Why only 2 loops? If looping is this incredible efficiency hack, why not loop 4 times or 16 times? We've seen other latent recurrent models try that.
Well, the authors actually profiled 3x and 4x loops. But what you have to remember is that you are operating under a strictly fixed compute budget. Every additional loop you add means you have to drastically shrink the model's width or depth to pay for it, so the wall clock time stays matched. They discovered that in the large-scale pre-training regime, the marginal benefit of recurrence decays very rapidly.
Ah, I get it. Because eventually, passing a representation through the exact same parameters a third or fourth time yields diminishing returns.
Yes, exactly.
But you sacrificed way too much hidden dimension width to afford it.
Precisely. They found that R equals 2 is the absolute sweet spot. It is the smallest, non-trivial recurrent setting. You get one ordinary transformation followed by exactly one local refinement step.
Which gives you the algorithmic benefits of iterative refinement without requiring you to cannibalize the model's base capacity.
It's all about maximum return on your compute investment.
All right, so the architecture is hyper-efficient, and they've built a phenomenally strong base model. Let's talk about the training data. They train it on 3 trillion tokens in stage 1, and then do a 1.26 trillion token high-quality annealing phase in stage 2.
And it's really worth noting for the engineers listening that in stage 2, they explicitly keep the learning rate constant.
But they don't decay it.
No, they avoid decaying it so the model remains highly plastic. That way it can maximize what it absorbs from that high-quality synthetic math and code data.
Right. But an efficient, knowledgeable base model doesn't automatically become a frontier-level reasoner. Usually, this is where you apply SFT, supervised fine-tuning, to teach it how to follow instructions and format answers.
Normally, yes.
But the authors completely abandoned traditional SFT. They introduced a massive paradigm shift called Supervised Pre-Training, or SPT. Now, wait a minute. If you are using supervised data, isn't that just fine-tuning? Why rebrand it?
It sounds like a rebranding, but the mechanics fundamentally change the training dynamics. To understand why SPT is necessary, you have to look at the massive drawbacks of standard SFT. You've probably seen SFT overfit firsthand. It suffers horribly from catastrophic forgetting. The model gets really good at adopting the specific conversational format of the fine-tuning data, but in the process, the gradient updates overwrite its general pre-training knowledge.
It learns to chat, but forgets facts.
Exactly. If you run SFT for more than 3 or 4 epochs, the model's general intelligence just collapses.
So how does supervised pre-training fix that? Because they are using the exact same token-level loss function as SFT, right? They mask out the prompt and context tokens, and only the target tokens, the actual answers, contribute to the loss.
They do use the same loss function, but the difference is the sheer scale of the optimization. SPT applies this supervised loss in a full pre-training regime.
Let's put some hard numbers on that for the listener, just to grasp the scale. A typical SFT run might process 128,000 to maybe 1 million tokens per batch, running over a total data set of 10 to 100 billion tokens.
That's standard, yeah.
SPT processes 128 million tokens per global batch.
It's massive.
And it runs over a colossal 2 trillion token budget, utilizing a sequence length of 131,000. It is a completely different universe of compute.
And that massive batch size is exactly why it solves catastrophic forgetting. When you run standard SFT with a small batch of 100K tokens, the gradient update is highly biased toward whatever specific instruction format happens to be in that tiny batch.
So the model overcorrects.
Yes. It shifts its weights aggressively to satisfy that narrow data, which causes the forgetting of broader concepts. But with 128 million tokens in a single batch, the gradient is a heavily smoothed average of thousands of different concepts, reasoning paths, and facts.
Ah, I see. So the model is forced to find a generalized weight update that satisfies everything simultaneously, rather than over-indexing on a single narrow task.
Exactly.
It's like the difference between cramming for a highly specific exam format versus actually learning the underlying subject matter.
That's a perfect way to look at it. Because the gradient aggregation is so broad, the authors were able to run SPT for 10 full epochs.
10 epochs on supervised data.
Yes. Standard SFT crashes and burns into overfitting by epoch 3. With SPT, there was zero overfitting. The loss just smoothly trended down. But the real breakthrough was the metrics.
What happened?
Not only did the math and reasoning scores explode, but the general pre-training metrics like ARC challenge and MMLU actually continued to improve throughout the entire supervised phase.
Wow. So it learned how to reason and format while actively getting smarter on general world knowledge. It proves that targeted supervision doesn't destroy general knowledge if you scale the batch size and token budget to pre-training levels.
It's a huge finding.
So with general knowledge and basic reasoning locked in, the final final step to forge what they call loopy thinking is reinforcement learning. This is what pushes it to those frontier math and coding levels.
Right. For the RL phase, they deploy an algorithm based on GSPO, which is Group Sequence Policy Optimization. They made a few critical tweaks here that are vital for ensuring stable RL at scale. First, they moved away from token-level clipping and implemented asymmetric sequence-level clipping.
Okay, usually in policy optimization, you clip the probability updates token by token so the model doesn't change its weights too aggressively and destabilize. What does sequence-level clipping change?
GSPO calculates a length-normalized importance ratio for the entire response. So all tokens in the same generated response share the exact same sequence-level weight.
Oh, I see.
This perfectly aligns the unit of optimization with the unit of reward, which is whether the final answer was correct or not. Furthermore, they use an asymmetric clip higher strategy.
So basically, asymmetric clipping is like a strict teacher grading a test.
How so?
If you take a wild guess and get the answer completely wrong, the teacher only docks you a standard amount of points so you don't get discouraged from trying.
Right.
But if you take a massive creative leap and get the hardest question right, they give you huge bonus points.
Oh, I like that.
It encourages safe exploration without heavily penalizing failure.
That's a great analogy. It allows the model to make much larger positive weight updates for exploratory responses that are highly successful while being mathematically conservative about penalizing negative responses. And they pair this with dynamic prompt filtering, which is just incredibly elegant.
I thought this detail was brilliant. Walk us through the filtering.
So during RL, a model generates a group of completions for a prompt. If a prompt generates a group where every single completion is correct or every single completion is incorrect, it provides zero relative preference signal.
Because there's nothing to compare it to.
Right. The advantage calculation basically centers to zero. It's useless for the gradient, meaning you are just burning GPU hours computing nothing. So the authors dynamically oversample and filter out those degenerate groups. The batch only contains groups with both successful and unsuccessful completions,
guaranteeing a highly useful gradient signal for every single update. No wasted compute at all. And the final benchmarks of this entire pipeline, the layer loops, the memory reinvested Loopie Recipe, the massive SPT, and the GSPO reinforcement learning are staggering. Loopie 20B A to B, which only uses 2 billion active parameters per token, was pre-trained on just 3.5 trillion tokens.
Keep the number in mind, 3.5 trillion.
Right. But they benchmarked it against NVIDIA's Nematron 3 Nano and Cascade models. Those are 30 billion parameter MOEs trained on an absurd 25 trillion tokens from the exact same data pool.
Loopie used less than 1/7 of the pre-training data.
And it beats them across the board.
Yep.
Loopie hits 81.28 on MMLU, exceeding both Nematron models. On ARC Challenge, it hits 93.52, beating Nematron 3 Nano and effectively tying the massive Cascade model. But in reasoning, it completely dominates. It hits 92.09% on the AME 2024 math competition benchmark and 94.21% on AMC.
It is wild, and it's also crucial to highlight the scalability here.
Yeah.
You didn't just tune one model to death and get a lucky seed.
Right.
They built a rigorous scaling ladder, training baselines from 0.15 billion all the way up to 1 billion parameters, and applied the exact same Loopie recipe at every single rung.
And did it hold up?
Across all 4 rungs, the compute-matched Loopie model consistently outperformed the non-recurrent baseline, and the performance gap actually maintained itself as the models got larger.
Which proves this isn't some small model artifact. The layer loop pattern and the width-depth recurrence trade-off are fundamental, scalable advantages.
Absolutely.
So, to recap the massive ground we covered today on this deep dive into the paper, we started with layer loops, proving that recurrence should be localized to prevent pipeline bubbles and respect the depth-varying representations of a transformer.
Yep.
We unpacked the Loopie recipe, showing how trading stored layers for microbatch efficiency lets you build a wider model that trains in the exact same wall clock time. We explored supervised pre-training, using 128 million token batches to entirely bypass catastrophic forgetting. And finally, we saw how GSPO reinforcement learning locks in frontier reasoning.
And that leaves us with a profound shift in how we think about the future of model architecture. I want you to mull over this final implication.
Oh, let's hear it.
If the Loopie architecture definitively proves that a transformer is actually more compute efficient when it recurrently refines a representation in the same layer, rather than endlessly passing it to brand new layers, what does this imply about the limits of traditional depth scaling?
That is a fascinating point.
Are we rapidly approaching a future where the trillion parameter models of tomorrow aren't actually thousands of layers deep, but are instead incredibly wide, shallow networks doing dozens of localized layer loops. And if that is the case, how might this massive paradigm shift change how we design inference time scaling and continuous reasoning moving forward?
That really is the trillion parameter question. Well, that wraps up today's discussion on AI Paper Slop. Thanks for tuning in, and we'll catch you next time.